Good morning, everybody. Mr. Ball, live from his house, ready to do a further maths lesson online. Very exciting times. So we are going to carry on finishing what we needed to do this year. You've got one more chapter left of pure maths, which is complex numbers and geometry. We've got a tiny bit left to do in numerical methods to do with order of convergence. So we'll get those done probably fairly quickly over the next couple of weeks, which means that we'll be finished early after Easter. So with that in mind, we will be, well, depending on what the situation is across the country, we might look into what we are going to do next. There's a couple of options currently which I'm thinking about. We can either start some of next year's topics. However, if we get too far ahead with next year's topics, then you won't have anything to do next year, which is a slight concern. We can obviously do some past papers, but I think we'll probably leave that till later and look at doing probably some mocks when we come back in September, I'm guessing, because I'm guessing we won't see each other before the summer. But if we do, then we'll try and do the mocks earlier. And so I think the other option we could possibly do is do something like further mechanics or further stats. So I'm having a quick look through those things at the moment, just seeing what I think. I'd rather not do further pure technology with you guys online because we require computers and other bits and bobs, and I'd just be a bit more comfortable doing that face-to-face as opposed to online. But if we did something like mechanics or stats, then and looked like we could get it done before the summer, or mostly done before the summer, that would mean that you guys would have 4 minor options altogether. You'd have modelling with algorithms, numerical methods, mechanics or stats, and you'd also do extra pure as well next year. So that would give you an opportunity to take 4 minor options in the exams next year, and the best 3 of those would count. So that gives us it'll give you a bit more wiggle room. At the moment next year, all you guys have got to study is the second half of the pure content and extra pure. So we've actually got probably slightly less content next year at the moment. There's lots of revision points already programmed in. So I'll talk to you more about those things when I know more. At the moment, it's all a bit of guesswork, and I don't have to make a decision for a few weeks at least. So what we're going to do in the next 3-4 lessons or so is we're going to do complex numbers and geometry. If you're wondering, I wasn't about to write geography, I was about to write GeoGebra because I've been playing with that this morning. So what we're going to do is start by looking at Argand diagrams, and I think you've probably seen Argand diagrams. I haven't actually got your textbook. I've got a few pictures of the chapter you guys are studying next, but I haven't got the textbook in front of me, so I'm not sure if you have or haven't. So I'll quickly fly through what an Argand diagram is, and then we're going to start looking at what the modulus and the argument of a complex number is. So just to remind you, hopefully, but maybe it's new, complex numbers obviously have a real part and an imaginary part to them. So they're numbers of the form x plus iy. So we could represent these in, well, what essentially looks like a Cartesian coordinate system. So if I say that this is the imaginary axis, and I say this is the real axis, where real numbers always have to just be on a number line. So here's a number line here. All real numbers lie on this line. Anything which has an imaginary part as well, we can say, well, it has to be up here somewhere. So let's say that this is the number x plus iy. X is, so it's x distance along the real axis. If I covered that up, it would be in the right place if I put it just on the axis. And then its y bit is here, so that's its imaginary part. So we can have numbers which have got the same real part, but lots of different variations of its imaginary part, and similarly we could have numbers which have the same imaginary part and lots of different real values to it. So that's how we do things in the complex plane. This is called an Argand diagram, just in case we haven't seen these things before. And one thing you may have noticed so far about complex numbers is when we talk about real numbers, it's very easy to say 6 is bigger than 5. It obviously is bigger than 5. You've known that since you were 3 or 4 years old, probably. With complex numbers, it's not so easy to say that 6 plus I is bigger than 6 minus I or something similar. It's not even obvious if that really means anything, to be quite honest. But what we can do is we can compare complex numbers in some ways. We can compare them by the distance they are from the origin. That's how we do it with real numbers. We say they have distance from 0. 6 is bigger than 5 because it's further away from 0 than 5. At least that works for positive numbers. If you're thinking about negative numbers, you have to be a bit more cute about it. And so we can do something with complex numbers. We can still talk about the distance away from the origin, and that can give us some idea of, not really size, but just a way of comparing them. So the way we can do that is by considering this distance here. So can you guys for me just do two things? Can you first of all consider this distance r in terms of x and y and tell me what it is? We'll write it down, I suppose. And can you also, just while we're at it, I'm going to put an angle theta in here. Can you also work out what that angle theta is in terms of x and y? And just pause the video and do that for me. So hopefully you thought about this in terms of right angle triangles. If the point here has distance r from the origin, well, this distance here is x, that distance there is y. So r squared equals x squared plus y squared, or in other words, r is equal to, I'm only going to take the positive value because it's a distance, r equals x squared plus y squared. And hopefully you managed to find theta as well. Theta we could do in terms of x and y. This is a right angle triangle as we've just used here. This is the opposite side, and the opposite side is length y. This is the adjacent side, x. Opposite and adjacent is tan. So tan of theta is going to be y over x. In other words, theta is tan minus 1 y over x. Okay, so with these we can do some things. We can do some things considering the distance that it is away from the origin, and we could also say, well, it's not only got a distance, we could also say how far round it is measured from the real axis if we use this idea of theta. And that's how we're always going to do it, and these two things have got very special names. So this first one, r, so the modulus of a complex number. You guys have come across the word modulus already in normal maths to do with functions. It doesn't mean the same thing, it basically means the absolute value of something. The reason why it's absolute value is because you basically square them and then square root them. It gives you the absolute distance it is away from somewhere. So the modulus, so z, so some complex number z is equal to x plus iy, then the modulus of z, use the same notation as we do in functions, is equal to the square root of x squared plus y squared. In other words, the real part plus the imaginary part coefficient. Okay, we don't have to put the I in there, it's just how far it is measured up the imaginary axis. Similarly, we've got, we can talk about the angle which is created by that modulus, and we call that thing the argument, which isn't necessarily obvious why. So the argument is, so z is equal to x plus iy, then the argument of z is equal to, now I'm going to write something slightly different to what you've probably imagined here, the angle created by the modulus. Let's assume the modulus is a line, for instance. It's not, but modulus line and the positive real axis. Okay, we don't generally draw a line from here to the complex number, but if we did, then the argument is the angle created by that line up here. Just put this up for a second so we can see a bit more. Created between this angle and the positive real axis. That's where we measure from. We don't measure from here, we don't measure from the imaginary axis, we always measure from the positive real axis. Okay, so one thing you're probably saying to yourself at the moment, or shouting at the screen, is, well, surely it's just this. And it is for half of them, and it's not for the other half. The reason for that is, well, actually, just before we go into that, let's just say something else. The argument is measured between minus pi and pi. Okay, we'll probably just take that equality out. Let's just say if it's all the way round, then it's going to be just pi. Now have you come across radians? Oh dear. Okay, quick crash course on radians for those who haven't done it. Radians is a way of measuring angles, and I suppose the simplest way to say this is that there is pi radians is the same as 180 degrees. So what the angles on a line add up to, 180 degrees or pi. Obviously therefore 2 pi is 360 degrees, or pi over 2 is 90 degrees, and any other thing, for instance. So a right angle is either 90 degrees, or you could say a right angle is pi over 2 radians. We're going to stop using the word radians, I think, from now on, because everything in this chapter is based upon using radians, not degrees. If that doesn't make very much sense, can you please email me so we can just deal with that. But I think some of you have seen it in physics already, and some of you have even seen it in normal maths actually. Okay, so the argument is always measured between minus pi and pi. We've already said that pi is 180 degrees. So this is the positive direction going around this way. So that way would be the positive direction. This would be the negative direction. So here would be pi over 2. If I measured an angle around here, it would be minus pi over 2, then minus 3 pi over 4. And then if we got round to this axis, if we went all the way around, we would probably say, we're going to say that that's pi, not minus pi. So that's the way we can measure an argument. Anyway, back to this idea. You're probably still thinking, well, why can't we use this one? Well, if you stick stuff into your calculator and do tan minus 1, it will always, always, always give you an answer between minus pi and pi. So if you haven't already, go to your calculator and just change it into radians, however you do that. So shift menu setup, angle unit, radians. So for instance, if I do shift tan of, let's think of one I know, 1 divided by root 3, I get 6 pi. What I could do is have, instead of something in this quadrant, because that would be in this quadrant, if I did 1 over root 3, I could have something in this quadrant instead. So that would be minus 1 over root 3 if it was the same numbers. Oops, lazy. Try that again. Root 3. And I get a minus 6 pi. So 6 pi and minus a 6 pi definitely aren't enough to get round to the axis. However, what happens if I had, I don't know, the complex number, if I had the complex number root 3 plus, well, so say minus root 3 minus 1. If I had minus root 3 minus 1, minus root 3 minus 1, that would be over here somewhere. The problem is, though, with that, is that if I then stuck it into this calculation, I'd have minus 1 over minus root 3, and I'd want to take the tan minus 1 of that. But those minuses cancel out just to give you the same as 1 over root 3. So it's just going to give you the angle in here again. And so we have a slight issue with that. So when you're doing these sorts of questions, you can use this idea, but you have to be careful afterwards to add a pi or take away a pi because it needs to be shifted by 180 degrees. Or better still, draw the diagram, work out what, use a right angle triangle in one of the quadrants, and then you can crack on from there. So for instance, if I was to do this example, so if I was going to say let z be equal to, let's go for one which is going to come up with a nice answer, minus root 3 plus I. So if z is minus root 3 plus I, if I draw myself a picture of this, if I find my pencil first, that would be useful. There we go. If I draw myself a picture, I'll quickly realise which quadrant it's in. Minus root 3 plus I, so that's going to be over here somewhere. That's minus root 3. This is plus 1. And if I draw a line, go into it, what I can do is quite easily work out what this angle is in here. So let z equal minus root 3 plus I. The question would be something like, find the modulus of an argument. Modulus an argument of z. It doesn't matter which quadrant it is in for finding the modulus. We can do that really quickly. Z is equal to minus root 3 squared plus 1 squared square rooted. That squared gives me 3, that squared gives me 1, 3 plus 1 is 4, square rooted gives me 2. And then if I want to find the argument, well, if I find out what theta is, I know tan of theta is equal to, the opposite side is 1, over the adjacent side is minus root 3. And so what I need to do now is, oh, sorry, I'm being silly. So assume when you're doing this, instead of thinking about negatives and positive values, yes, this is minus root 3, but let's just think about the size of this triangle. This triangle in absolute terms, the opposite side is 1, and the length of the adjacent side is root 3. Let me just get rid of that minus sign. Sorry, I'm being daft. And so what I can then do is tan of 1 over root 3. And if I work out what that is, and tan minus 1 over root 3 is going to be pi over 6. So I know theta is pi over 6. And if theta is pi over 6, then how many pi's have I got left here? Well, it's going to be Therefore, the argument of z is pi, because this whole distance is pi, take away that angle in there, which equals 5 pi over 6. So you can think about this a different way, always just using tan and coming up with some rules for when you add or subtract pi, and that uses things like cast diagrams. Yes, you can do it. However, if you do it and you get it wrong in the exam because you just say, oh, I need to add it because it's in that quadrant, you're more likely to go wrong. If you draw a picture, find out with the angle, and then do this, you will be right every time, as long as you don't make a small mistake. So I definitely think this is the safest way to do it, and definitely will keep your understanding as strong as possible. So can you guys quickly just do the following for me? Can you just do 2 examples? So try this one first. A really simple example. Let z equal 4 plus 3i. Can you find the modulus and the argument? And can you also do z equal to minus 1 minus root 3 I, and find the argument and modulus of that one too? So just pause the video and have a go at those, please. Okay, so let's see how you guys got on. So for the first question, 4 plus 3i, we've got this diagram here. That distance is 4, that distance is 3. The modulus is easy to find. The square root of 3 squared plus 4 squared is equal to 5. It's a Pythagorean triple. And then if I want to find out this angle here, I don't actually have to do an awful lot of work because this is already measured from the initial line, from the positive real axis. If I say initial line, that's another way of describing this bit. So tan of theta is equal to the opposite side, which is 3 over 4. So theta equals tan minus 1 of 3 over 4. Please make sure you stick that extra line of work in and don't be lazy. I haven't got room here, so that's approximately 0.644 radians. This one's a bit more fun. So the modulus of z is equal to the square root of minus 1 squared. You'll probably notice that these minuses you don't really need to have in here. Minus 3 squared. So that's 3 plus 1 is 4, so the modulus of this one is 2, unsurprisingly, because we've done one very similar to this already. Tan of theta, I need to define theta. It's up to you which one you pick. I would always pick this one because then it's easier to do overall. If you did this one, you'd have to add pi over 2 on, it just makes it unnecessarily more tricky. So tan theta is the opposite side. The opposite side is minus root 3. Well, actually, let's say that again. This side here is length of root 3. And this side has a length 1. So if I want to find theta now, I can just do tan minus 1 root 3 over 1. And tan minus 1 over root 3. If you remember your GCSE work, tan over root 3 is 60 degrees. 60 degrees is a third of 180, so it's the same as a third of pi. You'll find the more you use radians, the more you start to think in radians. It's sort of like learning a new language. Eventually you have dreams in French if you learn French for long enough. So theta is pi over 3. However, that's not the argument. The argument is actually this measure here. So the argument of z is equal to, right, this is where people make mistakes. Because we're going this way round, we would say the argument is negative. So that's negative pi all the way around to here. But then I need to plus back on pi over 3. Minus pi plus pi over 3 is 2 pi over 3. Please make sure you're very careful about that stage. To help put the minus sign there, wouldn't it? Okay, So hopefully those two things went well. What we're going to do now is start looking at something called modulus argument form, and then I'll finally stop talking. This video has been rather long. So modulus argument form. So obviously we've got our standard form of a complex number, x plus iy. But we could, now we know what the modulus is and how to define the argument, we could describe a complex number in terms of modulus and argument instead. So the best way to show you how to do this is by just doing this for a standard one here. So let's just draw that diagram we've drawn so many times already today. So here's a complex number, z equals x plus I, y. Let's say that the modulus is r and the argument is theta. So let's see what I can get out of this. Well, I could say, well, I know that this length here is y. I know this length here is x. So I can say that sine theta is equal to opposite over hypotenuse, which was y over r. Can you guys just quickly tell me what cos theta is? Cos theta is the adjacent over the hypotenuse, so that's x over r. Therefore, y is equal to r sine theta, just by rearranging this one, and x is equal to r cosine theta. So together what we can say is, well, if z is some complex number x plus iy, then it could also be, using these two here, z could be r cosine theta, by replacing x with this, plus I lots of r sine theta. We've got an r in both of these terms, so we can factorise it out to get r cos theta plus I sine theta. And this is what we call the modulus argument form of a complex number, because it's a complex number given in terms of its modulus and its argument with some trigonometric functions in there. Okay, so hopefully it's obvious now that if you know what a complex number is, you could write it in this modulus argument form by finding out what the modulus is and what finding the argument is. And we've just done that just over the page here. That's what we're doing there. And one thing which people sometimes totally lose is, if I gave it a modulus argument form, could you find it in x plus I y form? And sometimes people just think, oh god, how on earth can I do that? Well, you just calculate what these things are. If you calculate what sine theta is and times it by r, then you've got something times I. And if you've got cos theta times r, you've got something without an I in it. That puts it back into x plus I y form. So just find out all these numbers and multiply the brackets out. Can you guys now have a go at the exercise in your book? Let me try and remember which one it is. It's exercise 5.1. Can you try and do all of those questions? I know there's only half an hour left of today's lesson, but you know, you've got half an hour now and you should be doing some homework as well still. So can you try and do all of those? I would try and get them all done. Let's be honest, you can't really go out too much at the moment, so what else are you going to do? And I will speak to you guys again tomorrow, Tuesday tomorrow, and we'll look at multiplying and dividing complex numbers. And when we're doing it in modulus argument form, it's in some ways it's quite a bit easier than doing it in x plus I y form. Hope you have a nice day, and I'll speak to you again tomorrow. Bye bye.